Right now there is an object flying through our solar system that did not come from here. It came from another star. It is older than our sun, older than Earth, older than almost everything we can see in the night sky. And a few months ago, the James Webb Space Telescope pointed straight at it and pulled out data that scientists did not expect. This is only the third object like this ever found in human history. Before you keep watching, hit subscribe, because I'm about to walk you through exactly what Webb found, piece by piece, and why some of the world's top astronomers are calling this one of the most important discoveries of the decade. Let's get into it. On July 1st, 2025, a telescope system called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, picked up a faint moving dot in the sky. ATLAS is a network of telescopes built to scan the sky every night, looking for anything that could be dangerous, like an asteroid heading toward Earth. Host nights, it finds ordinary rocks. But this object was different. Its path through space did not match anything that belongs to our solar system. It was not orbiting the sun the way planets, asteroids, and comets do. It was just passing through on a straight line, coming from deep interstellar space and heading back out again. This object was given the name 3I Atlas. The number 3 means it is the third confirmed interstellar object ever detected. The letter I stands for interstellar, and Atlas is simply the name of the telescope system that found it. If that naming convention sounds unusual, it is because we have only needed it twice before. The first interstellar object we ever found was called 1A Oumuamua, spotted in 2017. It was strange, elongated, and it sped up in a way scientists still argue about today. The second one was 2I Borisov, found in 2019, which behaved much more like a normal comet. Now we have a third one, and this third one turned out to be the most chemically strange of all of them. Here is why that matters. Every comet and asteroid inside our solar system formed from the same original cloud of gas and dust, the one that also formed the sun and the planets about 4.5 billion years ago. That means almost everything we have ever studied up close, every comet, every asteroid, every icy moon, all came from the same neighborhood, the same raw material, the same starting point. An interstellar object breaks that pattern completely. It formed around a different star in a different part of the galaxy, under different conditions, and then got kicked out of its home system, probably by the gravity of a large planet, and has been drifting through the emptiness of space for possibly billions of years before it happened to cross paths with our solar system. So when scientists get the chance to study one of these objects up close, they are not just looking at a rock. They are looking at a physical sample of material from a completely different star system, something we could never otherwise collect. That is why the moment 3I Atlas was confirmed as interstellar. Telescopes around the world turned toward it, including the most powerful space telescope ever built, the James Webb Space Telescope. Let's talk a little more about those first two interstellar visitors, because they set the stage for how big a deal 3I Atlas turned out to be. Oumuamua was spotted only after it had already passed its closest point to the sun and was on its way back out, which meant astronomers only got a short window to study it, and with weaker tools than what we have today. It showed no clearly visible coma, no obvious tail, nothing that immediately marked it as a comet, and its brightness changed dramatically as it tumbled through space, suggesting it was unusually long and thin compared to typical solar system objects. Its motion also sped up slightly in a way that pure gravity alone could not fully explain, which is part of why it became the subject of so much public speculation. Most scientists believe that subtle push came from gas quietly leaking out of the object as it warmed, similar to how a comet behaves, just too faint to detect directly with the technology available at the time. Borisov found 2. Years later, looked and behaved much more like a familiar comet, with a visible coma and a chemical makeup fairly close to what we see in our own solar system's icy bodies, though it did carry unusually high levels of carbon monoxide. Neither of those two objects gave scientists nearly the level of chemical detail that 3I Atlas eventually would, mostly because, this time, we had Webb ready and waiting. Before we get to Webb's data, it helps to understand the object itself a little more. Early observations, including images from the Hubble Space Telescope, allowed scientists to put limits on its size. The nucleus, the solid icy core at the center of the comet, is estimated to be smaller than about 2.8 kilometers across, based on how much light it reflects. Unlike Oumuamua, which had almost no visible gas or dust around it and caused years of debate about what it even was. 3I Atlas immediately showed clear signs of being an active comet. It had a coma, which is the fuzzy cloud of gas and dust that surrounds a comet's nucleus when it gets warmed by sunlight, and even hints of a tail. In other words, this one behaved like a comet is supposed to behave, which already made it easier to study than Oumuamua ever was. But scientists also went back through old archived data from other telescopes and satellites to see if 3I Atlas had been active even earlier than expected. Data from NASA's TESSA satellite, which normally hunts for planets around other stars, had actually captured the object passing through its field of view months before it was officially discovered. That earlier data suggested the comet may have been releasing gas even when it was still more than 6 times farther from the Sun than Earth is, at a distance where it should have been far too cold for most ices to turn into gas. That early activity was one of the first hints that this comet was not behaving like a typical solar system comet, and that something unusual was going on with its chemistry. 3I Atlas made its closest approach to the Sun, called perihelion, in October 2025. This is the point where a comet gets the most sunlight and heat, and where the most dramatic activity usually happens, since the Sun's warmth turns frozen ice directly into gas, a process called sublimation. It then made its closest approach to Earth on December 19, 2025, though even at its closest, it stayed a very safe distance away, giving astronomers a valuable window to study it without any danger. Now here is where the James Webb Space Telescope comes into the story properly. Webb is not a telescope that looks at things the way our eyes do. It is built to detect infrared light, which is a type of light we cannot see, but which carries huge amounts of information about temperature and chemistry. When astronomers point Webb at a comet, they are not just trying to get a nice picture, they are trying to break down the light coming from that comet into a spectrum, which is basically a chemical fingerprint. Different molecules, like water, carbon, dioxide, carbon monoxide, and methane, each absorb and emit infrared light at very specific wavelengths. By reading that spectrum carefully, scientists can figure out exactly which gases are pouring off the comet and in what amounts, without ever needing to send a spacecraft to touch it. Webb's first detailed look at 3I Atlas happened in August 2025, while the comet was still approaching the Sun. Using an instrument called NIR-SPEC, short for near-infrared spectrograph, astronomers captured a spectrum of the comet's coma. What T? A found immediately stood out. In a typical solar system comet, water ice is usually the dominant material that turns into gas as the comet warms up. Water is, after all, the most common ice found in comets that formed in our own solar system. But 3I Atlas was doing something different. The data showed that carbon dioxide, not water, was the dominant gas coming off the comet by a huge margin. The actual numbers are worth hearing because they show just how extreme this is. Scientists calculated the mass loss rates for each gas, which basically means how many kilograms of that gas the comet was releasing into space every second. Carbon dioxide was being released at about 129 kilograms per second. Water was only about 6.6 kilograms per second. Carbon monoxide came in at around 14 kilograms per second. In percentage terms, that means carbon dioxide made up around 87% of the total gas being released, while water only accounted for about 4%, with the rest mostly being carbon monoxide. To put that in perspective, in a typical comet at a similar distance from the Sun, you would expect water to be the main gas, not carbon dioxide, making up the overwhelming majority. Scientists described 3I Atlas's carbon dioxide to water ratio as roughly 16 times more extreme than what you would expect from an ordinary comet at that same distance from the Sun. That is not a small difference. That is a comet behaving in a way that does not match anything we regularly see close to home. Why would that happen? One leading explanation has to do with how and where this comet originally formed. In a very cold, distant environment, especially one far from a young star's heat, carbon dioxide ice can become trapped and preserved more easily than in slightly warmer environments, where it might have escaped over time. A comet that formed in an extremely cold outer region, then spent a very long time drifting through the freezing emptiness of interstellar space, could end up chemically different from a comet that formed and stayed within a warmer, more active solar system like our own. In other words, the chemistry itself was becoming a kind of time capsule, hinting at the environment this object came from long before it ever reached us. After its closest pass by the Sun, the comet had been freshly warmed and its ancient ice had turned into an even brighter cloud of gas, giving Webb a perfect opportunity to look again, this time in more detail. So in December 2025, astronomers used Webb once more, this time relying heavily on another instrument called MIRI, the Mid-Infrared Instrument, to capture new spectra on December 15th, 16th, and 27th. This second round of observations delivered one of the most exciting results of the entire mission. For the first time ever in any interstellar object, scientists detected methane. Not water, not carbon dioxide, but methane, the same gas found in natural gas here on Earth, and a molecule that is considered highly volatile, meaning it turns into gas at extremely low temperatures. Finding it here was a big deal, because it had never been confirmed in an interstellar object before. This was the first direct detection of methane on any object known to have come from outside our solar system. The amount of methane being produced was measured relative to the amount of water vapor also being released. In the first of the 2 December observations, methane production was about 13.7% of the water production rate. By the second observation, just under 2 weeks later, that number had risen to about 27%, meaning the methane output had roughly doubled in a very short period of time. Scientists also noticed something else interesting. The methane did not show up right away, even in the earlier August dating. Its appearance seemed delayed, only becoming clearly detectable after the comet had already passed its closest point to the Sun and started heating up further. That delayed onset raised new questions about the internal structure of the comet, including whether the methane had been buried deeper inside the nucleus, only reaching the surface and turning to gas once enough of the outer layers had been stripped away by solar heating. Alongside methane, the December data also picked up a spectral signature from nickel, a heavier element rarely confirmed so clearly in cometary gas, adding yet another layer of chemical detail to the picture scientists were building of this object. It also helps to understand exactly what these 2 Webb instruments are actually doing, while pointed at something as faint and distant as a comet passing through our solar system. NIRSpec works by splitting incoming near-infrared light into a detailed spectrum, almost like passing sunlight through a prism, except far more precise and tuned to wavelengths our eyes cannot see at all. MIRI goes even further into the infrared range, into wavelengths tied closely to heat itself, which makes it especially good at picking up gases like carbon dioxide and methane that show their clearest signatures in that part of the spectrum. Neither of these instruments takes a normal photograph in the way we usually think of a picture. Instead, they produce a graph, a line that rises and d-dips at very specific wavelengths. And every dip or spike on that graph corresponds to a specific molecule absorbing or releasing energy. Reading that graph is how scientists were able to say, with real confidence, exactly which gases were present around 3I Atlas, and roughly how much of each was being released, all without ever needing to send a spacecraft anywhere near it. By comparing the August data to the December data, researchers also noticed that the ratio between carbon dioxide and water had changed. In August, before perihelion, carbon dioxide massively dominated the outgassing. By December, after the comet had already swung around the Sun and been heated intensely, that ratio had dropped to roughly half of what it was before. That kind of shift, watched directly with real data from 2 different points in the same koan. MET's journey gave scientists an incredibly rare, direct look at how an interstellar object's chemistry evolves as it interacts with a star's heat over time. This is something that is almost impossible to study with objects F from our own solar system, because comets that regularly pass close to the Sun have usually already been warmed many times before, softening these kinds of dramatic shifts. But the most surprising results were still to come. And this time they were not just about which gases were present, but about the actual atomic makeup of the ice itself. In a study led by astrochemist Martin Cordner of NASA's Goddard Space Flight Center and published in the journal Nature on June 22, 2026, researchers used Webb's NIRSpec instrument to look at something called isotope ratios in the KU MET's water. Isotopes are versions of the same element that have a different number of neutrons, which gives them slightly different weight. In the case of hydrogen, there's a heavier version called deuterium, sometimes nicknamed heavy hydrogen, which forms heavy water when it bonds with oxygen instead of regular hydrogen. The amount of deuterium found in a comet's water can act almost like a fingerprint of the temperature and environment where that water ice originally formed. Colder, more ancient environments tend to trap and preserve higher levels of deuterium. Warmer, more processed environments tend to convert more of that heavy water back into ordinary water over time. When Webb's TAO's team analyzed 3I Atlas, they found deuterium levels roughly 30 times higher than what is typically found in comets from our own solar system. That is an enormous difference, and it strongly suggests that this comet formed in an extremely cold environment, and that its ice was never significantly warmed or reprocessed after it formed, all the way until it eventually reached our Sun. Before we move further into the isotope story, it is worth going back to those early hints of activity, because they turned out to matter a lot. Researchers digging through archived data found that the Rubin Observatory had actually captured faint images of 3I Atlas as early as June 2025, weeks before its official discovery, when the comet was still more than 4 astronomical units from the Sun, meaning more than 4 times the distance between Earth and the Sun. Even further back, the TESS satellite had recorded the object nearly continuously from early May through early June of 2025, when it was still about 6.2 astronomical units away, and its brightness during that stretch stayed constant in a way that suggested gas was already escaping from its surface. And that is unusually early for a comet to start showing activity, since at that distance, the temperatures are normally far too cold for most familiar ices to turn into gas. It hinted, long before Webb ever got involved, that this object's ice was made of something more volatile, something that could sublimate at much colder temperatures than plain water ice, which is exactly the kind of behavior that carbon dioxide and eventually methane would go on to explain. Ground-based telescopes also tracked the comet's brightness closely in the days right after its discovery. Observations from the SOAR telescope in Chile, taken across a handful of nights in early July 2025, recorded dozens of brightness measurements and captured 2 short, independent brightening events, moments where the comet flared up briefly before settling back down. Around the same time, telescopes including the European Southern Observatory's Very Large Telescope and the Canada-France-Hawaii Telescope confirmed clear cometary activity in deep, stacked images. All of this groundwork, done by observatories across the world in the weeks after discovery, helped scientists build a timeline of exactly how active this comet was and when, long before Webb turned its instruments toward it for the detailed chemical readings that would follow. The team did not stop there. They also examined the ratio between 2 versions of carbon, the common carbon-12 and the much rarer, heavier carbon-13. Over the history of the galaxy, generations of stars have lived, died, and enriched their surroundings with heavier elements, including carbon-13. Systems that formed more recently, like our own solar system, which formed about 4.5 billion years ago, tend to have picked up more of this heavier carbon over time. But 3I Atlas showed only traces of carbon-13, far less than expected for a young system. That pointed toward one conclusion. This object formed a very, very long time ago, before the galaxy had accumulated as much of that heavier carbon. Based on all of this data together, the research team estimated that 3I Atlas may have formed somewhere between 10 and 12 billion years ago. To put that into perspective, our entire solar system, including Earth, the Sun, and every planet, is only about 4.5 billion years old. That means this comet could be more than twice as old as our own solar system. Scientists believe it likely formed during a period sometimes called cosmic noon, an era in the universe's history when star formation was happening at its most intense rate, inside a young star system that was probably sitting in a cold, dense cloud of gas and dust, far colder than the environment that formed our own sun and planets. Around the same time as Webb's findings, a separate research team, using the European Southern Observatory's Very Large Telescope, led by astronomer Cyrielle Aupetom of the University of Edinburgh, studied the comet's carbon and nitrogen isotopes in a molecule called cyanide, adding another independent line of evidence that supported the picture of an old, distant, chemically unusual origin for this object. One of the scientists involved in the Webb study, Stephanie Milam of NASA Goddard, explained why this kind of research matters beyond simple curiosity. Finding these rare isotope patterns is not just about chemistry for its own sake. It connects to one of the biggest questions in science: how common and/or rare are the conditions that could lead to life somewhere else in the galaxy? Right now, Earth is still the only place we know of where the right chemical ingredients came together to create life. Every time scientists study material from outside our solar system, like this comet, they are gathering a tiny piece of evidence to help answer whether our own story is common across the universe or incredibly rare. Now, if you have spent any time online, you may have already seen wild headlines about 3I Atlas. Some outlets and social media accounts have pushed the idea that this object might not be a comet at all, but something artificial, even suggesting it could be an alien probe. Part of this idea comes from a small number of scientists, most notably Harvard astronomer Avi Loeb, who has publicly raised the possibility that this object's unusual characteristics deserve serious consideration as a potential technological artifact, and who has written extensively online tracking the data as it came in. It is true that Loeb is a real astrophysicist, and it is true that he has raised these questions in public writing. But it is important to be clear about where the mainstream scientific community stands. The vast majority of astronomers studying 3I Atlas, including the teams behind the Webb and Very Large Telescope studies, interpret all of this data, the carbon dioxide, the methane, the deuterium, the carbon isotopes, as entirely consistent with a natural comet, just one that formed in an unusually old, unusually cold environment very different from our own solar system. Nothing in the chemical data itself points to anything artificial. It points to ice chemistry and cosmic history. There was even a direct search for any kind of artificial signal. In December 2025, around the time of the comet's closest approach to Earth, the Breakthrough Listen Project, a well-known scientific effort dedicated to searching for signs of extraterrestrial technology, used this massive green bank telescope to scan 3I Atlas across a wide range of radio frequencies. They were looking for any kind of unexplained radio signal that might suggest artificial technology on board. The result of that search was a clear non-detection. meaning no unusual signals were found, down to a very sensitive power level. In plain terms, one of the most capable technosignature search programs on Earth pointed its equipment directly at this object during its closest pass by our planet, and found nothing that would suggest anything other than a natural object. So where does that leave us? As of now, 3I Atlas is continuing to move away from the Sun on a path that will eventually carry it back out of our solar system entirely and into interstellar space once again, just as it came in. It will likely never return. This was very probably humanity's only chance to study this particular object up close, using every major telescope we could point at it in the short window it was here. What makes this story worth remembering is not some fictional secret or cover-up. It is the real scale of what was actually discovered. A physical object, drifting through our solar system, that most likely formed around a different star, in a different region of the galaxy, somewhere between 10 and 12 billion years ago, long before our own sun even existed. An object whose ice never fully thawed until it finally reached our sun for the first and only time. An object that gave scientists a direct physical sample of chemistry from an ancient corner of the galaxy, something that could never have been collected any other way. And an object studied by the most advanced space telescope ever built, using nothing but careful analysis of infrared light, turned into a detailed chemical story about ice, cold, time, and the deep history of our galaxy. It is also worth pausing on just how hard it actually is to study something like this at all. 3I Atlas was never anywhere close to Earth in the way the Moon or even nearby asteroids are. Even at its closest approach in December 2025, it stayed a very safe, very large distance away, and for most of the time it was observed, it was hundreds of millions of kilometers from us, far beyond. Where sunlight is strong and far beyond where most instruments can pick up detailed signals easily. Estimating the size of its nucleus from that distance is genuinely difficult, because astronomers cannot simply look at it and measure it the way you would measure an object sitting in front of you. Instead, they measure how much sunlight it reflects, combine that with a SUMI, patience about how reflective its surface is likely to be, and use that to calculate an upper limit on its size. Observations using the Hubble Space Telescope helped narrow that down, suggesting a nucleus smaller than about 2.8 kilometers across, though the true size could be meaningfully smaller once the surrounding coma of gas and dust is accounted for. That kind of careful, layered detective work, combining data from multiple telescopes, multiple instruments, and multiple research teams around the world, is really what this entire story has been built on. It is easy to see why headlines exaggerate stories like this one. A comet flying in from another star, dripping with strange chemistry and unusually heavy isotopes, is genuinely dramatic material, even without adding anything false to it. But the honest version of this story does not need exaggeration to be worth telling. Real astronomers, using real telescopes, pulled a detailed chemical history out of a faint point of light hundreds of millions of kilometers away, and used it to make a genuinely reasonable case that this object formed more than 10 billion years ago, in a part of the galaxy far colder and far older than anything close to our own solar system. That is not a small claim. That is one of the oldest, most well-traveled physical objects human beings have ever gotten this close a look at. There is also a bigger, quieter point sitting underneath all of this. Every time an interstellar object passes through, even briefly, it becomes a kind of test for our own instruments and our own science. Oumuamua tested us with almost no data at all and left more questions than answers. Borisov gave us a more familiar comet to compare against our own solar system's chemistry. And 3I Atlas, thanks to better timing, better preparation, and the incredible sensitivity of Webb, gave us the most detailed interstellar chemical story so far. One detailed enough to talk about deuterium ratios, carbon isotopes, and a likely age measured in billions of years, not just guesses about shape and speed. If a fourth interstellar object is ever found, and most astronomers expect one eventually will be, this entire event becomes the baseline. It shows exactly what modern telescopes are capable of pulling out of a target that is moving fast, far away, and only passing through once. That is the real story of 3I Atlas. Not a hidden signal, not a cut feed, not a cover-up. Just real data, gathered honestly, that turned out to be more incredible than almost any conspiracy theory could invent on its own. A visitor older than our sun, passing quietly through our solar system, leaving behind nothing but light for us to read. If you found this breakdown interesting, subscribe for more deep dives into real space discoveries, explained clearly, using actual data from real missions like Webb, Hubble, and the teams of scientists working on them every day. There's a lot happening in space science right now that is genuinely stranger and more exciting than fiction. Thanks for watching, and I will see you in the next one.